Good afternoon, everyone. In the previous session, we have started Laplace transformation. We have completed Laplace transform definition, formulas, first shifting theorem, problems based on first shifting theorem, then definition of Heaviside unit function. Then we have completed second shifting theorem, as well as problems based on second shifting theorem. Now today we will start change of scale property. This is the next topic of this unit, that is change of scale property. Now let us have the theorem and proof of this change of scale property, and then we will have problems based on this. Let us write the theorem statement now. If Laplace of f of t is equal to f bar s, comma, then Laplace of f of at is equal to 1 upon a f bar s upon a. This is the statement of change of scale property. Now this is the statement. Now we'll do the proof based on this. Now let us have proof. Here it is given. What is given? First we write given L of f of t. Given L of f of t is equal to integral 0 to infinity e power minus st f of t dt, that is equal to f bar s. This already you know. This already we have learned in the previous sessions. Now let us so here first L of f of t is equal to f bar s we have written, which is given. Then we have to prove L of f of at is equal to 1 upon a f bar s by a. So we write here L of f of at is equal to integral 0 to infinity e power minus st, and then in the place of f of t we have f of at. So we write here f of at and then we write dt. Then after this we have to write this is equal to, because here we have f of at. Now we will take a substitution, like we write here let at is equal to x. This implies t is equal to x by a. Now when you differentiate t, that becomes dt is equal to dx upon a. Now this we substitute in the given, then this is equal to integral 0 to infinity e power minus s into, in the place of t we have to substitute x by a. So x by a into f of x into dx by a. So here in the place of t we have substituted x by a, in the place of at we have substituted x because we have taken at is equal to x. Then in the place of dt we are substituting dx by a. So now this is equal to, now I can take 1 by a outside. If you take 1 by a outside, then integral of 0 to infinity e power, I can write this as minus s by a into x into f of x dx, because I have taken this a outside and then we have written this way. So this is equal to 1 upon a. Now this is in the form of f bar s by a. As you know, f bar s is equal to integral 0 to infinity e power minus st f of t dt. This is also equal to what? Laplace of f of t is equal to f bar s is equal to this one. So here whatever s we have, here we write here. Now you can see here we have e power minus s by a into x f of x dx. So we can write f bar s by a. Whatever in the previous we are writing f bar s as integral 0 to infinity e power minus st f of t dt. So here we are writing f bar s by a. So hence the proof. So this is the proof of the given change of scale property. I hope you have understood. Let us have most of you are saying that. So now it is clear now. Now you can see once again I want to read this change of scale property we are doing today here. Now the theorem statement is nothing but if L of f of t is equal to f bar s, comma, then L of f of at is equal to 1 upon a f bar s by a. So now in the proof what we do, first we write L of f of t, that is integral 0 to infinity e power minus st f of t dt, which is equal to f bar s. Then now it is asked to prove L of f of at is equal to 1 upon a f bar s by a. So we take here Laplace of f of at is equal to integral 0 to infinity e power minus st. In the place of f of t we have to write f of at dt. Now we are taking the substitution here. Substitution is nothing but at is equal to, here whatever at we have we are taking at is equal to x. Then from this t is equal to x by a. That you differentiate both sides, that becomes dt is equal to dx by a. Then integral 0 to infinity e power minus s. In the place of t I am substituting x by a into f of at. So in the place of at I am substituting x here, and in the place of dt I am substituting dx by a. Then afterwards I am taking this 1 by a outside. So 1 by a integral 0 to infinity e power, I am writing this minus s into x by a as minus of x s by a into x into f of x dx. Then 1 by a. Then as you know the formula, that's nothing but L of f of t is equal to integral 0 to infinity e power minus st f of t dt. So here we have integral 0 to infinity e power minus s by a into x into f of x dx. So instead of writing f bar s, we have to write f bar s by a, as we have in the place of s we have s by a, so we write f bar s by a. So hence proved. So this is the proof of change of scale property. Now let us do problem based on this. Now first we write here problems. Here now I am writing first problem. First problem is given Laplace of f of t is equal to s square minus s plus 1 upon 2s plus 1 whole square into s minus 1. It is given. Now applying change of scale property, show that L of, that is Laplace of f of 2t is equal to s square minus 2s plus 4 upon 4 into s plus 1 whole square into s minus 2. Now we have to show this one. Now for solving this, first we write solution here and we write given. What is given here? First we write given L of f of t is equal to, now you can see L of f of t is given s square minus s plus 1 upon 2s plus 1 whole square into s minus 1. This is given. Now this can be considered as I have told you, L of f of t is equal to whatever function we have, that is in terms of s. So we write f bar s. After writing that, now we have to apply change of scale property to show that L of, that is Laplace of f of 2t is equal to, we have to show this one. So for showing that, we have to write Laplace of f of 2t is equal to, now because as you have seen in the change of scale property proof, that is nothing but Laplace of f of at is equal to 1 upon a f bar s by a. So we have to write Laplace of f of 2t is equal to 1 upon 2 f bar s upon 2 from change of scale property. As I have shown just now, L of f of at is equal to 1 upon a f bar s by a. Okay, so after writing this is equal to, now 1 upon 2, now into, now here you have f bar s by 2. We know f bar s is nothing but s square minus s plus 1 by 2s plus 1 whole square into s minus 1. Wherever s we have to substitute s by 2. So then this becomes s by 2 whole square. Here we have s square, so we have to write s by 2 whole square minus, again we have s, so we write s by 2, then we have plus 1 upon, now here we write 2 into s by 2 plus 1 whole square into s by 2 minus 1. So in f bar s we have substituted in the place of s as s by 2. So after this we have to simplify this one. If you simplify, this becomes, here you can see 1 upon 2, and if you put bracket here, now I can write this as s square by 4 minus s by 2 plus 4 upon, you get, here you can cancel this 2 and 2, so this becomes s plus 1 whole square, and then we have s minus 2 upon 2 we get. When you take the cross multiplication, So you get s minus 2 by 2. So now then close the bracket. Then after closing the bracket, now just simplify, like you take the LCM now. Now if you take the LCM here in the numerator, you have 4 LCM. LCM is 4, so s square minus 2s plus 4 you get upon 4 upon you get s plus 1 whole square, and then you have s minus 2 upon 2. Then close the bracket. Then afterwards you can write this as this is equal to 1 upon 2, and then you can write this is nothing but s square minus 2s plus 4 upon 4, and then you just write this in numerator. If you write this in numerator, this becomes s plus 1 whole square into s minus, so you can write 2 upon s plus 1 whole square into s minus 2. So now you can cancel this 2 and 2, then this becomes 1 upon 4 into, in numerator you can see you have only s square minus 2s plus 4 upon, now you have write the denominator, that is s plus 1 whole square into s minus 2. So this is the answer which is asked to find now. Here you can see L of f of 2t is equal to s square minus 2s. Now you just compare our solution here, s square minus 2s plus 4 upon 4 into s plus 1 whole square into s minus 2. Now after solving we got the same, 1 upon 4 s square minus 2s plus 4 upon s plus 1 whole square into s minus 2. So in this way we solve the problems based on change of scale property. So if you want, let us take another problem, otherwise we'll take a next topic. We'll have I'll give you some more problems in PDF. Now let us have next topic today. So we have completed change of scale property, as well as we have completed problem based on that. Now let us have next topic. Next topic is Laplace transform of derivatives. This is next topic. Today when we have started with change of scale property. We have proved the theorem based on that, and then we have done one problem. Now we'll go for next topic, that is change of scale Laplace transform of derivatives. Let us have the theorem statement. Here also we have a theorem, so let us write this theorem statement. Let us write here, if f dash t be continuous, and Laplace of f of t is equal to f bar s, then L of, that is Laplace of f dash of t, is equal to s into L of f of t minus f of 0. This is the theorem statement. This topic is nothing but Laplace transform of derivatives. Okay, now let us have the proof of this one. In this proof, first we write what is given. As you know, given, or we know L of f of t is equal to integral 0 to infinity e power minus st f of t dt. As I have told you, this will come in the entire topic, the entire unit. Now here you should you should remember this. Laplace of f of t is equal to integral 0 to infinity e power minus st f of t dt. Now we have to find what? Laplace of f dash t. For finding Laplace of f dash t, now when you write Laplace of f dash t is equal to integral 0 to infinity e power minus st. In the place of f of t, we have to write f dash t here, f dash t dt. Okay, so after writing this, now you can see here we have integration uv, integral of uv dv. So we have to use integration by parts formula now. As you all aware of that formula, now let us directly write based on that formula. That is nothing but you get here u is nothing but e power minus st, then integral of f dash t. So differentiation and integration get cancels, you get only f of t here. Then limits are 0 to infinity. Then we write minus. Now we'll have integral first. So integral 0 to infinity. Now we will differentiate now d by dx of u, that is u dash, you will have u dash, u is nothing but e power minus st. When you differentiate e power minus st, you get minus s into e power minus st. When you differentiate e power minus st, you get e power minus st. Again, when you differentiate minus st, you get minus s. You are integrating with respect to t here, remember. Now we have integral of v dx. So if you integrate f dash t, you get only f of t, because differentiation and integration get cancels. Then we'll have dt here. Then after this, where you apply the limits, now here we have infinity. Upper limit is infinity. When you apply infinity to t, that becomes e power minus infinity. As I have told you in the previous classes, that e power minus infinity is 0. 0 into something is 0. So I can write 0 here. Then minus lower limit. If you apply 0 to t, here it becomes e power 0. E power 0 is 1. 1 into f of t is, and here we are substituting 0 to t. So when you apply here 0, so e power 0 is 1, and here f of, in the place of t we are substituting 0, so f of 0, you will get only f of 0. Then plus, now minus into minus plus, so you take s outside, then put integral 0 to infinity, then e power, what is remained here, e power minus st is same as it is, into f of t dt. Now you can see this is equal to, now you have f of minus f of 0 plus s into, now this whole term is nothing but, you have written here L of f of t is equal to integral 0 to infinity e power minus st f of t dt. In the place of integral 0 to infinity e power minus st f of t dt, we write only L of f of t, that is Laplace of f of t. Okay, so now this s into L of f of t, we have started from L of f dash of t. Okay, then I can write this as Laplace of f dash t is equal to, I am writing the positive term before, so this becomes s into L of f of t minus f of 0. So hence proved. This is the theorem which we have proved just now. This is Laplace transform of derivatives. Okay, so now let us have before starting the problems based on this, let us write note. So note 1 is nothing but Laplace of f double dash of t is equal to s L f dash of t minus f dash of 0. So now that is also equal to, when you solve this becomes s square Laplace of f of t minus s into f of 0 minus f dash of 0. This is nothing but Laplace of f double dash of t, because when you substitute Laplace of f dash of t as s into L of f of t minus f of 0 here, then you have to multiply with s, so that it becomes s square L Laplace of f of t minus f of s into f of 0 minus f dash of 0 is same as it is. So this is note 1. So in the same way, when you take for Laplace of f triple dash of t, then Laplace of f power 4 of t and so on, we will write in general Laplace of f power n of t is equal to s power n Laplace of f of t minus s power n minus 1 f of 0 minus s power n minus 2 f dash of 0 and so on minus f power n minus 1 of 0. So when you write Laplace of f power n of t, you will get s power n Laplace of f of t minus s power n minus 1 f of 0 minus s power n minus 2 f dash of 0 and so on minus f power n minus 1 of 0. So this is Laplace transform of derivatives up to nth. Now let us do the problems based on this. First problem is if Laplace of sine root t is equal to root pi upon 2 into s power 1 by 3 by 2, 3 by 2 into e power minus 1 upon 4s, comma, find Laplace of cos root t upon root t. We have to find this one. In order to find this one, first we write in the solution what is Laplace of, we have to find Laplace of f dash of t here. So for finding that, we have to find this one by taking Laplace of f dash of t. Now first we write f of t. What is f of t first? So it is given in the problem. If L of this should be considered as f of t is equal to root pi by 2s power 3 by 2 into e power 1 upon minus 1 upon 4s. So here f of t is nothing but sine root t. Now we write from f of t, if you differentiate f of t, that becomes f dash t is equal to, where you differentiate sine root t, that becomes cos root t. When you differentiate root t again, that becomes 1 upon 2 root t. Now where you substitute f of 0, that is in the place of t 0, then this is equal to sine 0. Sine 0 is equal to what? 0. Now we use the formula Laplace of f dash t. Laplace of f dash t is equal to, as you know, as we just proved, s into Laplace of f of t minus f of 0. So here Laplace of f dash t, we have just got this from f of t, so we write here in the place of f dash t as Laplace of cos root t upon 2 root t is equal to s into Laplace of f of t is given here in the question, that is root pi upon 2 into s power 3 by 2 into e power minus 1 upon 4s minus f of 0 is nothing but 0. Now we have substituted in the formula, then we simplify this one. When you simplify this, this is equal to, I just take out this by 2, 1 by 2 outside, so this becomes 1 upon 2 Laplace of cos root t upon 2 root t. Then when you take 1 by 2 outside, you will get the same. Now after that, I take this numerator s to denominator here. This becomes s power 3 by 2 into s power minus 1 into e power minus 1 upon 4s. Minus 0 is, just leave that neglected. Now after that, you can write this as, now here you can cancel 2, yes, you can cancel 2, then this becomes Laplace of cos root t upon only root t, we should not write 2 here again, so root t. Okay, so now this is equal to, now here I can write root pi upon, this is, we don't have 2 here, only cos root t by root t, so because we have taken out 2, so we have cancelled 2 here, so now root pi upon, here basis same, power should be added. If you add powers, then this becomes s power 3 by 2 minus 1, that is nothing but s power 1 by 2 into e power minus 1 upon 4s. Now I can write this as Laplace of cos root t upon root t is equal to, now s power 1 by 2 I can write root s, so I can write this as root pi by s into e power minus 1 upon 4s. This is the solution of the given problem. These problems are very important for the exam point of view, and as well as the theorem proofs are very important. So the thing is, you have to remember all these statements as well as proof of the given topics what we have studied just now, and these are the problems based on the given topic. Now let us have second problem based on this. Second problem is, if Laplace of t sin wt is equal to 2 ws upon s square plus, instead of w write omega square whole square, comma, evaluate number 1. First problem is Laplace of omega t cos omega t plus sine omega t. So this is the first problem. This is the first bit. Now second bit is Laplace of 2 cos omega t minus omega t sine omega t. Now let us do this problem, first bit and second bit. Now these are the solution for first bit now. So let us first find before that let us have what is given here. Now let f of t is equal to, now you can see here, as I have shown you in the previous problem also, here if it will be given like L of f of t is equal to f bar s. So we have to consider f of t is equal to what? T sine omega t. Then when you differentiate this, then this becomes sine omega t. If you differentiate sine omega t, you will get what? You have to apply uv dash. Now when you apply the formula, then you get omega t cos omega t plus sine omega t. Now when you differentiate again, then this becomes f double dash of t is equal to, again here you just take omega common, then t into cos omega t, again uv formula. So when you put omega outside, then this becomes, when you differentiate cos, you get minus sine omega t. So you get, after differentiating cos omega t, you get omega t sine omega t plus, now here you get cos omega t. I have used uv formula for t cos omega t here, putting omega common, plus when you differentiate sine omega t, then you get w cos omega t. So after differentiating, if you simplify and if you write this, then this becomes f double dash of t is equal to, now when you multiply this, you get minus omega square t sine omega t, then plus omega cos omega t plus omega cos omega t. So then if you simplify this, you can see here omega cos omega t plus omega cos omega t. So you can write 2 omega cos omega t minus omega square t sine omega t. So this is nothing but f double dash of t. So after writing f double dash of t and f dash t, now just I'll put 0 in f of t, f dash of t and f double dash of t. Then it becomes f of 0 is equal to, when you put 0 in t here, t into t, if you put 0 here, 0 into something is 0, okay, then f dash of 0. So when you put in the place of f dash of t, in the place of t 0, then the whole term becomes 0, because here t, in the place of t we are putting 0, 0 into something is 0, sine 0. Here you can see t, in the place of t, if you put 0, sine 0 is 0. So f dash of 0 is also 0. Then when you put 0 in f double dash of t, now this is f double dash of t. Now you can see 2 omega cos omega, in the place of t you are putting 0, so cos 0 is 1. So you will get 2 omega here. Now here in the place of t, if you put 0, 0 into something is 0, so you will get only 2 omega in f double dash of 0. Now we will take first bit. So first bit is Laplace of f dash of t. We will prove that by taking this Laplace of f dash of t is equal to, you know the formula, that is s into Laplace of f of t minus f of 0. Now Laplace of f dash t, what we got here? Omega t cos omega t plus sine omega t. The place of f dash t I am writing this one. Now is equal to s into Laplace of f of t. It is given in the problem. What is given? Given Laplace of f of t is equal to 2 omega s by s square. I'll write here 2 omega s upon s square plus omega square whole square. It is given in the problem. Minus f of 0 is nothing but 0. So we write 0 here. So then this is equal to, we get s 2 omega s square upon s square plus omega square whole square. So this is the solution for first bit. We got this. Now when you do second bit is nothing but Laplace of f double dash of t is equal to, so you know Laplace of f double dash of t is nothing but s square Laplace of f of t minus s f of 0 minus f dash of 0. Now when you substitute Laplace of f double dash of t, which we got here I write Laplace of 2 omega cos omega t minus omega square t sine omega t is equal to s square. As just now we have written Laplace of f of t is given 2 omega s upon s square plus omega square whole square minus f of 0 is 0, so I write s into 0 is 0 minus f dash of 0 we got 0, so we write 0 here. So solution is nothing but 2 omega s cube upon s square plus omega square whole square. So this is the solution for first bit and second bit. Hope you have understood, and this will get for 5 marks in the final exam. So this is the solution for this. So we'll have next problem now. Instead of doing next problem, we'll go for next topic now, because I already have completed 2 problems based on this topic. Now let us have next topic. Next topic is Laplace of Laplace transform of integrals. Now let us have the theorem statement. The theorem statement is, if Laplace of f of t is equal to f bar s, comma, then Laplace of integral 0 to t f of u du is equal to 1 upon s f bar s. This is the So this is the theorem, this is the theorem statement of Laplace transform of integral. Now let us have let us have note of this. We won't do proof for this one, only we'll write the statement of this Laplace transform of integral. Now note is nothing but, first note is, if Laplace of f of t is equal to f bar s, Laplace of f of t is equal to f bar s, comma, then Laplace of integral 0 to t f of u du, just close the bracket, this is equal to 1 upon s square f bar s. This is the note. You can see here, Laplace transform of integrals is nothing but, if L of f of t is equal to f bar s, then Laplace of integral 0 to t f of u du is equal to 1 upon s f bar s. Now here this note will have two integrals, 0 to t, 0 to t. If it is the case, then you will get 1 upon s square f bar s. Now in second note we will write in general, comma, Laplace of integral 0 to t and so on, integral 0 to t f of u du and so on du, then close the bracket, then this is equal to 1 upon s power n f bar s. Okay, this is for n terms, and you can see this is Laplace transform of integral. Now let us have problem based on this. So if you do the problem, you can understand this. So first problem is, find Laplace of integral 0 to t e power minus t cos t dt. Okay, this is the problem based on this. Now let us have a solution of this. Now if you do the problem, if you do the solution, now let us see here. First you observe in the problem it is given e power minus t cos t. Now first we have, it is in the form of, you can see, when f of t is accompanied with e power minus at or e power at, you have to assume that is from first shifting theorem. So first we write L of cos t. This is f of t. Laplace of f of t we find first. That is equal to, as you know, the formula of Laplace of cos at is nothing but s upon s square plus a square. So I write here s upon s square plus 1 square, that is 1, because a is 1 here. Now we got f bar s. Now when you apply first shifting theorem, that is, it is given Laplace of e power minus t cos t, that is equal to, now I can write this as, in bracket I write here f bar s. In the previous class we have studied this first shifting theorem. Now s changes to, here you can see e power minus at in the sense we have minus 1, so we can write here s plus 1. Now we got f bar s as s upon s square plus 1, close the bracket, and write here s changes to s plus 1. So after writing this, then in the place of s you have to write s plus 1. So you write s plus 1 upon s plus 1 whole square plus 1. Now when you simplify this, this becomes s plus 1 upon s square plus 2s plus 2. Now here we have to consider now this as f bar s, as you have taken here f bar s for solving the given in the first shifting theorem, and then after solving whatever function it is given here, after getting whatever solution at last you got resultant s plus 1 by s square plus 2s plus 2, that you have to consider now as f bar s, because here you can see Laplace of integral 0 to t f of u du is equal to 1 upon s f bar s. So whatever you got here, that is f bar s, now we directly substitute in the given theorem statement. Now let us have the result like now. Laplace of integral 0 to t e power minus t cos t dt is equal to 1 upon s f bar s, because we have only one integral, so we write 1 upon s f bar s. So equal to, now we have s plus 1 by f bar s, we got s plus 1 by s square plus 2s plus 2. So we can write this as s plus 1 upon s square plus 2s plus 2, and this s I am writing here. So this is the answer for this. First we have to see here what is given. So when it is given e power minus t cos t, we have solved in the form of first shifting theorem. Then whatever answer we got, that we have taken as f bar s. As you know from Laplace transform of integrals, Laplace of integral 0 to t f of u du is equal to 1 upon s f bar s. So when you have f bar s, now you can directly put that is equal to 1 upon s into f bar s. This is the solution for the given problem. Now let us have next problem. Next problem is find Laplace of integral 0 to t cos h at dt. Close the bracket. Now when you find the solution of this, now you can see we have f of t is nothing but cos h at. Now when you find Laplace of f of t, that is equal to Laplace of cos h at, you know Laplace of cos h at is nothing but s upon s square minus a square. So that is equal to, f bar s. In the previous problem it was based on first shifting theorem. Now in this second problem you can see it is directly given Laplace of cos h at. So you know the formula. Just in the first session I have given you the Laplace transform of elementary functions, so that from that we can write this one. So then now Laplace of integral of 0 to t cos h at dt is equal to, now we can write Laplace of this is equal to 1 upon s square f bar s. F bar s in the sense we have f bar s is nothing but s upon s square minus a square. So now you can cancel s and s here, so you get 1 upon s into s square minus a square. So hence the answer. Hope you have understood the second problem based on Laplace transform of integral. We have done two problems. So here you have to remember the theorem statement. There is nothing but formula. Then based on that formula we can write or we can do the problems based on that. So this is the second problem. Now let us have next topic. Next topic is, first we write here this one we use in next topic. So we write here Leibniz rule for differentiation under integral sign. If you know this topic, if you know this, then we can apply in next topic, which is multiplication by t power n. Now let us have what is given in Leibniz. What is Leibniz rule for differentiation under integral sign? We will write here first. That is, if f of x comma alpha and dou by dou alpha f of x comma alpha be continuous functions of x and alpha, then d by d alpha in bracket integral a to b f of x comma alpha into dx is equal to integral a to b dou by dou x f of x comma alpha dx. This is Leibniz rule for differentiation under integral sign. Now you can see here we have d by d alpha integral a to b f of x comma alpha dx, that is equal to integral a to b dou by dou x. Instead of writing d by d alpha here, we are writing dou by dou x inside f of x comma alpha dx. So this is a Leibniz rule which we use in the next topic, that is multiplication by t power n. Let us have that. Now I am writing here the next topic, that is multiplication by t power n. Now let us have the theorem statement now here. The theorem statement is if Laplace of f of t is equal to f bar s, comma, then Laplace of t into f of t is equal to minus d by ds f bar s. Now Let us prove this. Let us prove this now. Now, once you just go through the statement now, if Laplace of f of t is equal to f bar s, then Laplace of t into f of t is equal to minus d by ds f bar s. Now let us have the proof now. In the proof, first we write given. So given is nothing but Laplace of f of t is equal to f bar s is equal to integral 0 to infinity e power minus st f of t dt. So you know this. Now here when you differentiate f bar s, here you have f bar s. I am differentiating f bar s with respect to s. So this is equal to d by ds. I am differentiating on both sides with respect to s. Then this becomes integral 0 to infinity e power minus st f of t dt. Now after this, from Leibniz rule, first I'll show you Leibniz rule here. Here you can see d by d alpha integral a to b f of x comma alpha dx. We can write integral a to b dou by dou x f of x comma alpha dx. So here from Leibniz rule for differentiation under integral sign, using that I can write this as integral 0 to infinity. Instead of d by ds, I can write dou by dou s e power minus st f of t dt. Okay, so after writing that, this is equal to, now when you differentiate e power minus st with respect to x, so this becomes integral 0 to infinity minus t into e power minus st f of t dt. I am differentiating e power minus st with respect to x, so you got minus t e power minus st f of t dt. Now in next step, I can write this is equal to, I can take this minus outside, that becomes minus integral of 0 to infinity e power minus st into, I take t with f of t, so that this becomes t into f of t dt. Now you are well aware Laplace of f of t is nothing but integral 0 to infinity e power minus st f of t dt. In the place of f of t we have t into f of t, so I can write this as minus Laplace of t into f of t. Now after this we can write, here we have started from d by ds of f bar s, and we got that is equal to minus Laplace of t into f of t. So I can write this as, in the next step, Laplace of t into f of t is equal to minus d by ds f bar s. Now you can see here Laplace of t into f of t, this minus I have taken to other side and I have written here. So this is the required solution for the given proof. Hope you have understood. This is nothing but multiplication by t power n. First, it is given statement is nothing but Laplace of f of t is equal to f bar s. Then Laplace of t into f of t, we have to show minus d by ds of f bar s. First, we have to take Laplace of f of t. You know that. Now I am differentiating both sides with respect to x. That is nothing but d by ds of f bar s is equal to d by ds of, you get integral 0 to infinity e power minus st of t dt. So then, using Leibniz rule for differentiation under integral sign, I write integral 0 to infinity instead of d by ds. I have to write dou by dou s e power minus st f of t dt. Then integral 0 to infinity. Now when you differentiate e power minus st with respect to x, you get minus t into e power minus st f of t dt. This minus goes outside, e power minus st, and this t with, I am writing with f of t. This is nothing but in the form of Laplace. So I can write Laplace of t into f of t. Then this is equal to Laplace of t into f of t is equal to minus, I take to other side, that becomes minus d by ds of f bar s. So hope you have understood this. Now let us have a note based on this. We'll have a note now. You write here in general Laplace of t power n f of t is equal to minus 1 whole power n d power n upon d s power n f bar s. Now you can see this is Laplace transform of t power 1 f of t. Now the same way we can write for n, Laplace of t power n f of t is equal to minus 1 whole power n d power n by ds power n into f bar s. So based on this we'll have a problem. Let us have a problem now. The first problem is find Laplace of t cube e power minus 3t. This is the problem given here. Now first we find Laplace of f of t, and then we use the formula Laplace of t power n f of t. So here first we write the solution. F of t given, f of t is equal to e power minus 3t. Now when you apply Laplace for f of t, this is equal to Laplace of e power minus 3t. This is equal to, as you know, the formula, since I write here Laplace of e power minus at is equal to 1 upon s by 1 upon s plus a, 1 upon s plus a. So I write here from this formula Laplace of e power minus 3t is equal to 1 upon s plus 3. So after finding Laplace of f of t, now we apply the formula, since Laplace of t power n f of t is equal to minus 1 whole power n d power n by ds power n f bar s. Now here you can see in the given problem n is 3 here. So when you substitute in the given problem, so I write n is nothing but 3. As we can see It is given in the given problem as it is given in the problem. Laplace of t cube f of t is nothing but e power minus 3t. We have to find now. This is equal to minus 1 whole power 3 d power 3 upon d s power 3 f bar s. F bar s, you know. F bar s we got 1 upon s plus 3. Now, in the next step, as you know, minus 1 whole cube is nothing but minus. And if you differentiate 1 upon s plus 3 once, then here you can write d square upon ds square. Now I can write this as equal to minus 1 upon s plus 3 whole square. As you know the formula, d by dx of 1 by x is minus 1 by x square. I am differentiating once, you got this. Again when you differentiate minus d by ds, you get, because we are differentiating again for this term. So minus of minus, this become plus, and then here you get minus 2 upon, when you differentiate 1 upon s plus 3 whole square, you get minus 2 upon s plus 3 whole square. Now when you differentiate this, the whole term, again this becomes 6 upon s plus 3 whole power 4. I am using here the formula of d by dx of 1 by x. When you use the formula of d by dx of 1 by x, we can write that is equal to minus 1 by x square. So I have differentiated this term again and again, so that you got the answer 6 upon s plus 3 whole power 4. So this is the solution for the given problem. Now let us do next problem. Next problem is second problem. Find Laplace of t sine square 3t. Now I'll give you the hint. It is helpful for you. If you do this as homework, then it will be better for you. I'll give the hint for this. You do at home. So here I'll give the formula which will be used here. That is nothing but sine square 3t. As you know, f of t is nothing but sine square 3t. So sine square 3t is equal to 1 minus cos 6t upon 2. So you can use this as f of t, find the Laplace, that becomes f bar s. Then you can find the solution as we did in the previous problem. Hope you will do this. Now let us have next topic, that is division. This is the hint for you. First you find, here we have t power 1, n is 1 here. This is f of t. You can take f of t as you take 1 by 2 outside, then you will get Laplace of 1 minus Laplace of cos 6t. Then when you solve this, then you will get f bar s. That f bar s you just substitute in the formula, that is Laplace of t into f of t. Then you will get the answer. Hope you will do that. Now we'll write the next topic, that is division by t, small t. division by t. The previous topic was multiplication by t power n. This is division by t. So remember, whatever we are studying today are very important for your final exam. So concentrate this, practice more and more problems so that it will be easy for you. So now the theorem statement is, if Laplace of f of t is equal to f bar s, comma, then Laplace of f of t upon t is equal to integral s to infinity f bar s ds. Laplace of f of t by t is equal to integral s to infinity f bar s ds, provided the integral exists. Now let us have the proof for this. So let us have the proof. Now here first we know what is given here. Laplace of f of t is given. So Laplace of f of t, you know, that is integral 0 to infinity e power minus st f of t dt. That is equal to, we write f bar s. Now after this, now we have to write, we will take this one, I will show Laplace of f of t by t. So I write here integral of s to infinity f bar s ds is equal to integral, because as you know f bar s is nothing but integral 0 to infinity e power minus st f of t dt. So here already we have one integral, so that I write first integral s to infinity, and in the place of f bar s, I am writing this one. So then this becomes integral 0 to infinity e power minus st f of t dt, into, again here we have ds, so we write here ds. So after writing that is equal to, now I can write that as integral 0 to infinity, I just take out f of t, I am writing here f of t dt here, and then I write integral s to infinity e power minus st ds. Now you can see here I am taking this f of t dt 0 to infinity outside, then s to infinity e power minus st ds here. So after that is equal to, now when you integrate e power minus st with respect to x, then that becomes integral 0 to infinity f of t is as it is, you have to write, into here if you integrate this becomes e power minus st upon minus t. As you know, we have a formula, integral of e power ax dx, that is e power ax by a, as we are integrating with respect to s here, so we get minus t here in the denominator, then limits are s to infinity. Okay, so now after that this is equal to, now when you apply the limit, then I can write that as integral 0 to infinity f of t into, I write dt outside afterwards, so I can apply the limit here, upper limit minus lower limit. When you apply lower limit and upper limit, then this becomes e power minus infinity minus e power minus st upon minus t. Then close the bracket here, then you write dt. Then after writing this, I have applied upper limit, then lower limit. Limits should be applied to s here, as we are integrating with respect to s here. So when you apply infinity here, e power minus infinity it becomes, then s to s, so this becomes e power minus st upon minus t. So the result I'll write here. So that is nothing but integral 0 to infinity f of t. Now e power minus infinity is 0 minus e power minus st upon minus t you get. So I write directly, that becomes e power minus st upon t, because minus minus get cancels, you get only e power minus st by t. So after this you can write this as, this is equal to integral 0 to infinity e power minus st. I'm writing here first, then I take this t to f of t, that becomes f of t by t dt. I'll take the pen. Then this is equal to now you can see here, this is integral 0 to infinity e power minus t into f of t by t dt. Now when you recall this formula, Laplace of f of t is equal to integral 0 to infinity e power minus st f of t dt is equal to f bar s. So here in the place of f of t you have f of t by t. So I can write from this as Laplace of f of t upon t. This is the formula for Laplace of f of t by t, because Laplace of f of t is nothing but e power integral 0 to infinity e power minus st f of t dt. So here when you compare that, from that we can write Laplace of f of t by t. So hence the proof. So we have started from integral s to infinity f bar s ds is equal to Laplace of f of t by t. So this is the proof for that. So based on this we'll have problems tomorrow. Now you can post your attendance now. Hope you have understood. I request you all, don't send or don't post your attendance twice or thrice. Post your attendance once. Tomorrow we'll start the problem based on this division by t, and then we'll go for next topic, that is inverse Laplace transforms. So by today we have completed Laplace transform, that is first part of this unit. Then we have inverse Laplace transform, and then we have third part is applications. So let us start tomorrow inverse Laplace transform. So I request you all to go through the notes, practice that, so that you can easily understand whatever I'm teaching here. Thank you.